Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study Math, Science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 1 Force. We will be discussing the topics Moment of Force and Equilibrium and also solve numericals from this chapter. Hope you all are ready to the class. Yes, let's begin. Force is a word we all are familiar with from our smaller classes. Here I have a pen. I am keeping this pen on my hand. This pen is at rest now. Okay. How can I move it? What should be done? I can push the pen. Okay. On pushing, the pen starts moving. That is, the pen is brought into motion. Okay. Is there any other option? Yes. I can pull the pen. On pulling, what happens? The pen is brought into motion. In simple words, we can define force as a push or pull on an object is called force. Opening a door is an example. What we are doing? We are pulling the handle. Yes, we are pulling the door. Then closing a door, shutting a door. This is again an example. Now give me some examples. Examples of force. So these are all examples of force. Yes, tug of war. In this, what the children are doing? They are pulling. They are applying a force. They are pulling the rope. Okay. Here we have door. This door is opened. How is the door opened? Somebody should come and pull the handle. Only then the door gets opened. Now to shut the door, what should be done? It should be pushed. Okay. Here a child is being sitting in a cart and a boy is pulling from one side. Another girl is pushing from one side. So here both of them are applying forces. Okay. So for examples, give me some examples now. Examples in your daily life where force is applied. 1. Kicking a football. Kicking a football. Then pushing a table. Pushing a table. Then hitting a cricket ball. Any other examples? Yeah, we can write this example. That is closing a door. Closing a door. Slapping a person. Okay. Slapping a person. In all these cases, what we are doing? We are applying a force. So, force is any push or pull. Okay, got a simple idea about force? Yes. Let us see what are the effects of force. Now, I have a ball with me. Okay, what I am going to do is, I am going to press this ball. What happened when I press this ball? Is there any change? To press this ball, I have applied a force. Applying a force, I am pressing this ball. Okay, I am squeezing this ball. What happened now? The shape has changed. Correct. The shape has changed. Then what else? It was in a spherical shape. It has been squeezed. It has changed its shape. Anything else? Size has changed. It has become smaller, right? The bigger ball has become smaller when I pressed it, when I squeezed it. Okay. Anything else? Its volume has also changed. So, if you keep this bowl inside a vessel or some utensil, initially, it will be occupying this much space. But when you press this and keep it, when you squeeze this and keep it, what happens? The space occupied reduces. Yes. So, what do we understand from this? A force can change the shape of an object. Okay. Then, it can change the size of an object. Here, our bowl has become smaller. Then, force can change the volume of an object. Only this much. A force can change state of rest or state of motion of an object. You remember? That is a body. That is, we took the example of a pen. A pen which was held in my hand is now at rest. What happens? When I apply a force, when I push it or pull it, what happens? The body is brought into motion. Similarly, if I take this ball and just roll it, what happens? It comes to motion. That is, a body at rest comes to motion. Okay. Now, a ball that is rolling, if I just go and keep my hands like this in front of the ball, what happens? It comes to rest. So, a body in rest can be brought into motion and a body in motion can be brought into rest. Okay. Force changes the state of rest or state of motion of a body. Next example, next effect is, here you can see a girl kicking a food bowl. Okay, initially let's say the bowl was rolling like this. This is how the bowl was coming. This is the direction of motion of the bowl. Okay, what happens? The girl comes and kicks from here. What happens to the ball? The direction changes. Okay, it starts moving in a different direction. It should have moved in this direction, but from a girl, an external force is being applied and the direction changes. So the next is, force changes the direction of motion of an object. Okay, so the 5 points to remember: force can change the shape of an object, it can change the size of an object, it can change volume of an object, then it can change the state of rest or motion, it can change the direction of motion of a body. Clear? So these are the 5 points. Next, let's see what is a unit of force. Force has both magnitude and direction. A quantity which has both magnitude and direction, what do we call that quantity? It is a vector quantity. We have taken many examples. Force, that is, in which direction we are applying force. According to that, it changes, right? The effect of force can change. It can change, that it changes with, it depends on the direction and also on the magnitude. How much force we are applying and in which direction it is being applied. Okay. Therefore, force is a vector quantity. Okay, clear? Now, according to Newton's second law of motion, you remember Newton's laws of motion? What is the first law? A body remains in a state of rest or uniform motion along a straight line unless an external unbalanced force acts in the direction of force. Second law, the rate of change of momentum is directly proportional to force. And the third law, favorite law, what is it? For every action, there is an equal and opposite reaction. Here we need only the second law. The statement is, the rate of change of momentum is directly proportional to force. Okay. F proportional to d by dt of p. D by dt means rate of change of, okay, rate of change with respect to time. How is a quantity changing? That is d by dt. D by dt of p. What is p? P is our momentum. What momentum? It is a linear momentum. So we can say that force is the rate of change of linear momentum. Okay. In order to remove this proportionality, what is done? A constant k can be introduced. Okay. K dp by dt. Now what is p? What is momentum? Momentum is the product of mass and velocity. We'll be having p is equal to mv, where m is mass and v is velocity, linear velocity. Okay, m into v. We can write this as F is equal to k d by dt of mv. Now tell me, is m a constant? For a given body, mass is a constant, so it can be taken out. Velocity can change with time. Okay, this can be written as k m dv by dt. Okay, now here, what is dv by dt? Rate of change of velocity. What is rate of change of velocity? We know that velocity is rate of change of displacement. And rate of change of velocity is acceleration. Rate of change of velocity is acceleration. So this can be written as kma. Okay, for a convenience, let us take this k a constant as 1. F is equal to ma. F is equal to ma. Force is equal to mass into acceleration. So here we understand that from the second law of motion, we get the equation for force. F is equal to ma. Now we need the unit of force. Yes, it is made up of, it is a product of mass and acceleration. What is the unit of mass? Standard unit of mass. Kilogram. Correct. What about acceleration? Acceleration we know is velocity by time, and velocity is displacement by time. Displacement unit is meter, unit of time is second. The unit of velocity is meter per second. Okay, acceleration is velocity by time. That is meter per second divided by second. That is equal to meter per second square or ms raised to minus 2. Okay, we'll be getting kilogram meter per second square or kilogram ms raised to minus 2. But we have accepted another unit for force, which is Newton. Okay, Newton is the unit of force We know the unit of energy is joules. It is derived from a scientist's name. Okay. Similarly, from Sir Isaac Newton's name, we have a unit for force, which is Newton, represented as capital N. Now remember one thing, while writing the unit name, you should never use capital letter N in the first. Okay. Newton. This is the wrong way of writing. This is how you will write a unit. Okay. First letter should be a small letter. This means it is the scientist's name and this is a unit. Okay. What is the unit of force? Unit of force is Newton, represented as capital N. Okay. Or another unit is kilogram force. Even this way you can represent the unit of force, kilogram force. Okay. 1 kilogram force will be equal to 9.8 Newton or G Newton. What is G? Yes. Acceleration due to gravity. G is the acceleration due to gravity and its value is 9.8 meter per second square. Okay. 1 unit of force is kilogram force. Okay. Kilogram force means 1 kilogram force will be equal to G newtons or 9.8 newtons. Clear? So this is an idea about the unit of force. Got it? Let us come to the topic. We need to understand what is motion and the types of motion. Here, motion is change in position of a body with time. Okay. A person is at point A. He should reach a point B. What will he do? Either he can walk or he can move in a scooter, whatever it is. That is, when time changes. Time changes. Time is never a constant. It will always change. When time changes with respect to time, if the position of a body changes, then the body is said to be in motion. Okay. A person was standing here. In 15 minutes, he had moved to a position B. He reached here. Okay. With respect to time, let us say he has travelled some 0.5 kilometer. This 0.5 kilometer distance he has travelled in 15 minutes. Then we say that this body was in motion. Okay. A body at rest has come to motion. Clear? This is a basic idea about motion. Movement. Okay. Now, if I am moving this pen is initially at rest. What happens? When I am pushing, it is moving. The body is in motion. I am shifting from this place to this place. Yes, I have been in motion. With respect to time, what happened? I have changed my position. I was in motion. Clear? There are two types of motion that we are going to discuss. So, motion is of two types. Linear motion. Linear motion is also known as translational motion and rotational motion. Let's see in detail what linear motion is and what rotational motion is. Linear motion or translational motion. This is the first type of motion we are going to discuss. When a force acts on a stationary rigid body which is free to move, the body starts moving in the straight path in the direction of force. Take an example. I am standing here. Okay, some external agent, like somebody from outside is going to push me. What will happen? My position will change, right? I have been shifted to a new position. What happened in this case? My initial position was here. I have come to a new position. Let us say my initial position is A. I have come to B. What happened? Somebody was applying a force on me. Okay, a force is being applied in this direction. In the same direction, I have moved along a straight line. Okay, my movement was along a straight line. In this case, it is an example of linear motion or translational motion. I have undergone a linear motion or translational motion. Now take this example. A boy is having a ball. He is throwing this ball. How is the ball moving? This is the initial position. Here is the first position, second position, third position, fourth position. All these positions of the ball is along a straight line. Straight line. Okay. So this is again an example of straight line motion or linear motion or translational motion. Take another example. You have a table here. Okay, this is a table. A boy is pushing this table from here. What happens? The table will shift its position. That is, the table will start moving. How does it move? Along a straight line. Along a straight line, the body, here the table starts moving. Okay, this is again an example of translational motion or linear motion. Okay. Second one is rotational motion. If a body is pivoted at a point and the force is applied on the body at a suitable point, it rotates the body about the axis passing through the pivoted point. This motion is called rotational motion. Now take a case. Here I have a pen with me. I need to move this pen. Okay. By applying force, I can move this pen like this. Okay. This is a translational motion. Now what I am going to do is I am holding this point tight. Okay. Here I have held one point tight. One end is held tight. Now I am applying a force. Just look at it. What happens then? Here when applying a force, what is happening? Is a complete body shifting? Does all the particles in this body experience the force and move in the same direction? No, right? When I apply a force, what is happening? Only from this end it is rising. Okay? This end is remaining the same. There is no effect. But initially when I was lifting like this, what happened? All the particles are moving. Okay. So here I have a body. Applying a force, what happens? All the particles in the body is changing the position. Completely it is shifting like this. Okay. So this was a translational motion. Why? Because all the particles have changed its position. The second case, now what I showed you is, here one end is held tight. Okay. Applying force on any other point, what happens? This is how it moves. Okay. This is a new form in which it comes. In this case, we call it a rotational motion. So this point is a pivoted point, okay, where we are holding it tight. Take another example, okay, a stone which is tied to a thread. You are rotating it. What happens? The stone will be moving like this, okay. Stone will be moving. Here there is a center. This distance of the thread, the stone will be at some distance from the thread, okay, thread, the place where we are holding the thread. From our hands, it will be at a particular distance. This will be the same distance. The distance will be same at any point the stone reaches. Okay, here a rotation is happening. This is again example of rotational motion. Next, take the case of a fan. In case of a fan, the wings are moving in a rotational motion. Okay, initially it was here. So this point is the pivoted point. With respect to this point, it is moving. Now just imagine, we have A, B, C, 3 points taken. Okay, the particles which are here will be moving longer distances. It takes a complete circle. Okay, particles which are at point B, they don't take as much distance that is taken by particles which were at C. Okay, they will be moving only this much distance. With this much distance, they will be moving. If it is A, again, they are moving very small distance. Okay, that is the distance covered is very small. Opening a door. Opening a door. Here you have a handle. This is the hinge. Okay. What happens when I pull this door? How is it moving? It is showing a rotational motion. It is showing a rotational motion, right? So here I am holding this handle and I am moving. What happens? With respect to this, we have an axis. Along this, the motion is happening. The door will get opened. If I apply a force here to pull, will the body open? That is, will the door open? No, right? We can open the door only when a force is applied to any other points, not a point on this hinge. Clear? This is an example of rotational motion. Take the case of a wheel. What we are doing? Here there is a pivoted point. Okay. I am applying a force tangentially. Tangentially means just I am applying a force like this. What happens? The wheel starts moving. This wheel starts rotating. Again, rotational motion. This is an example of rotational motion. With respect to this point, the rotation is happening. Okay. At any point, if I am considering a particle here, it may reach any point on this circle. The distance from this pivoted point will always be same. Okay. Understood what is rotational motion and translational motion? Next very important topic is moment of force, or it is also called torque. What is torque? Torque, the turning effect on the body about an axis, is called torque. We know what a force is. Force is any push or pull, or it is the rate of change of linear momentum. Okay, when it causes, this force can give you a turning effect, then it will be called a torque. Okay, consider this case, opening or closing a door. Now here I have a book in my hand. This point is my pivoted point and I am holding it tight. I want to give it a rotational motion. What can be done? Where will I hold and move this? Yes, I'll be applying a force here. Okay, when I apply a force here, it is bringing a rotational motion. Okay, why have I chosen this point? Why not this point? What will happen if I apply a force here? Applying a force here, I can rotate it. Okay, even applying a force here, I can rotate it. Applying a force here, I can rotate it. Applying a force here, the rotation is very difficult. When I am applying force here, there is no rotation. So what did you understand from this? Here, let us take the case of this book. Okay. We applied force at 5 points. Let's say A, B, C, D and E. Except E, in all other cases, we were able to rotate. But what is the difference? Now just try this, or you can try with your door. Okay. Why do you always keep a handle at one end? It is at a longer distance from the pivoted point, right? From this axis of rotation, it is at a longer distance. Why is it happening? Now when I applied force, I am applying the same amount of force. Say, if I apply same amount of force, you can see this. That is, the rotation, the amount of rotation happening is different. Yeah, like when I apply a force like this, here it has moved more distance. But when force was applied to this point, distance moved has become less. Applied to this point, again less. Okay, now to move same distance, let's say here I am applying simple force. A simple push I am giving. Okay, this much distance I have to move. I am applying force here. I will be applying more force. I will have to give more force. Okay, so from this you will understand one thing. When force increases, rotation increases. Yes, when force increases, rotation increases. Just by giving a small push, it is rotating very small distance. But when I give a heavy push, what happens? When I apply more force, what happens? More amount of rotation. In more angle, the rotation is happening. So here, applying the force, amount of force applied, it depends. Okay. Now, the second thing on what it depends is, see here, we will have applied force at different point. When was it easy to move? When was it easy to rotate? When the force was applied at A. That is, I am applying force here. Yes, that is, the distance from this axis increases. Okay, the point of where the force is applied is at maximum distance from this pivoted point. Okay, from this axis. Clear? Okay, this is the same case with door. Why do we always go and hold the handle? Because your parents have taught you, when you open a door, you should catch the handle and pull it or push it. Is it the reason? Now you can teach your parents why we are doing like this. When you do like this, that is, when you hold your handle, what happens? Yeah, in small force, you can apply small force and open the door. But if you are applying force at somewhat a middle point, what happens? To open the door, you will have to apply more force. This is the reason. Understood? This effect, this turning effect is called torque. We understood one thing, that is, torque depends on the force applied and the distance of the application of force from the axis. Clear? From the pivoted point. Okay. Factors affecting the turning of a body. What are the two factors on which the turning of a body depends? So, the turning effect of a force on a body depends on the following two factors. First one is the magnitude of force applied. As we said, when force increases, what happens? The torque or the turning effect also increases. Force increases, moment of force or torque also increases. Next, the perpendicular distance of the line of action of force from the axis of rotation or pivoted point. Why perpendicular distance? Take a case, go near your door. Okay. How do you open a door? You will be always standing like this. Here you will be having a handle. Okay. And you will be pushing a door like this. Okay. This is my door and I am pushing the door. How am I applying the force? I am applying force at an angle 90 degree. So this is your door. Okay. And this is the force I am applying. The force always I am applying in 90 degree. Just check this. This angle is 90 degree. Angle between the force, applied force, that is my hand, and the door is 90 degree. Why 90 degree? Just try. You go and open a door like this. Just you are standing like this, okay, and you are pushing the door like this. Then what happens? It will be difficult. Try with some 30 degree angle. Okay, you are standing like this and pushing like this. It will again be difficult. At 60 degree, it will also be difficult. Okay, but the difficulty level will decrease. But when you push the door standing like this at 90 degree, what happens? It will be easier. Okay, you can just try this. So this is what the perpendicular distance of the line of action. Line of action is my hand. Okay, how the force is applied of the force from the axis of rotation. Axis of rotation, if this is the pivoted point. Okay, this is the axis of rotation. Okay, or that is the hinge of a door. When this distance is maximum, also the torque or the turning effect increases. So what are the factors? One, it depends on force, and also let's say R is the distance. Okay, distance of any point where the force is applied from the axis of rotation. When this distance increases, this is a perpendicular distance. Okay, perpendicular distance R increases, our moment of force or torque also increases. Okay, torque depends on the force applied, and that is the magnitude of force and the perpendicular distance. Perpendicular distance from the line of action. Clear? Next is how to measure torque. Measurement of torque. The moment of force is equal to the product of the magnitude of the force and the perpendicular distance of line of action of the force from the axis of rotation. As we said, torque depends on two factors. One is the perpendicular distance and second is force. Okay, therefore we can write moment of force or torque is equal to force into perpendicular distance. Okay, force into perpendicular distance. This is F into R. Now take a case. Here you have a body. This is point O. This is your pivoted point. Okay. I am applying a force here at a point A. This is how the force acts. When you draw perpendicular, let us say this is a perpendicular which we get from this pivoted point. We are calling it P. Okay. So this perpendicular distance and the force we have to take. So it will be the product of force and the perpendicular distance. Take an example. You have a door. Okay. 50 Newton force you are applying. 50 Newton force. Okay. In 2 points we are taking. Let us say this is point Q and this is point P. Clear? Here you have the pivoted point. Let's call it O. Let this distance be some 0.5 meter and this distance is 1 meter. Okay. Now tell me, we are applying equal force. Okay. At both the points we are applying equal force. In which case is the turning effect or the moment of force or torque maximum? At this point P or this point Q? Give me the answer. Q, correct. Why? Because this is at maximum distance. Here the perpendicular distance is maximum when we are pushing at this point Q. Here the distance is smaller. This is 0.5 meter and this is 1 meter. In the first case, what will be the torque? Torque. That is, we are considering the 1 meter distance. Point at 1 meter distance. What is the torque? Force into perpendicular distance. Force is anyway equal to 50 Newton. 50 Newton into distance is 1 meter. You will be getting 50 into 1, which is 50. Now, what will be the unit? Here, we said torque is the product of force and perpendicular distance. Unit of force is Newton. Perpendicular distance. Distance unit is meter. Therefore, the unit of torque is Newton meter. Okay. 15 Newton meter you will be getting. The torque in the first cases, that is point Q we are considering, torque will be equal to 15 Newton meter. Second case is with 0.5 meter distance, point P. What do we get? 50 into 0.5, which is 25 Newton meter. We are getting 25 Newton meter, which is greater. Yes, 15 Newton meter is greater. That is when the force is applied at this point Q. Understood? Okay. One more point. For producing maximum turning effect on a body by a given force, the force applied on the body at a point for which the perpendicular distance of the line of action of the force from the axis of rotation is maximum. This is what we said. Yes. Here the perpendicular distance, when it is maximum, turning effect will be maximum. Okay. Clear? This is how you can measure torque using force and the perpendicular distance. Take the product of force and perpendicular distance to get torque. And the unit is Newton meter. Let us take an example. A body is pivoted at a point. A force of 10 Newton is applied at a distance of 30 centimeter from the pivot. Calculate the moment of force about the pivot. How to calculate moment of force? We have moment of force or torque is equal to force into perpendicular distance from the axis of rotation. Okay. Torque is equal to F into R. Here what is F? Force is 10 Newton. Given force is 10 Newton. Then what else is given? Applied at a distance of 30 centimeter from the pivot. So the distance R is equal to 30 centimeter. Now what we need to do? We have to take the product. Is there something that is to be changed? Here it is given in 30 centimeter. It is given in units of centimeter. We need the standard unit. If force is in Newton, then distance should be in meters. So 30 centimeter should be converted into meters. We have 1 meter is equal to 100 centimeter, which means 1 centimeter is 1 by 100 meter or 10 raised to minus 2 meter. Okay. What about 30 centimeter? If 1 centimeter is 10 raised to minus 2 meter, then 30 centimeter will be equal to 30 into 10 raised to minus 2 meter. Okay. So R will be 30 into 10 raised to minus 2 meter. How many decimal points? 2 points. Okay. You will be getting 0.3 meters. R is 0.3. Now calculate the torque. What is the torque? Torque will be equal to force. Force is 10 Newton into R. R is 0.3 meter. 10 into 0.3 is equal to 3. You will be getting 3 Newton meter. Okay. The required torque to produce a turning effect, the torque is 3 Newton meter. Clear? Second example, a mechanic can open a nut by applying a force of 150 Newton while using a lever handle of length 40 centimeter. How long a handle is required if he wants to open it by applying a force of only 50 Newton? So here we have two cases. Okay. In the first case, force applied is 150 Newton. And in the second case, he can apply only a force of 50 Newtons. In both the cases, what is the aim? He need to open a nut. Both the cases, the torque will be same. Yes. What the torque we get in the first case will be the same as the torque that we get in the second case. Here, distance. What is the distance? A lever handle of length 40 centimeter. So here you have a nut and this is a lever handle, you see. Okay, this distance is 40 centimeter. R is 40 centimeter. What we need to find? We need to find how long a handle is required, the length of handle to open this nut. When a force of 50 Newton only can be applied. Okay, in this case, we need to find what R is. First step, convert this 40 centimeters into meters. How much do we get? 40 centimeter will be equal to 0.4 meters. Now tell me what is the torque in this first case. Torque is equal to force into perpendicular distance, which is 150 into 0.4. Okay, 150 into 0.4. You will be getting 60 Newton meter. 60 Newton meter is the torque. Again, in this case, the torque will be equal to 60 Newton meter in both the cases. To open a nut, 60 Newton meter torque should be applied. Find R from this. We have torque is equal to force into perpendicular distance R. Then what is R? R will be torque divided by force. Here the torque is 60 Newton meter divided by the force applied. Here the force applied is 50 Newton. Okay, zeros can be cancelled. 6 divided by 5. What is 6 divided by 5? We will be getting 1.2 meter. Okay, so 1.2 meter into centimeter. To get 1.2 meter in centimeter, you have to multiply with 100. Okay, 1.2 meter or 120 centimeter. So, the required length of handle will be equal to 120 centimeter when only 50 Newton force can be applied. Clear? Next is clockwise and anti-clockwise moment. If the effect on the body is to turn it anti-clockwise, the moment of force is called anti-clockwise moment. Okay, here I have a cello tab with me. Just look at it. To turn it anti-clockwise, we know what is clockwise and anti-clockwise. How does the needle inside a clock move? It will be moving in clockwise direction. So, this direction is clockwise direction. Okay, and the opposite direction. This is anti-clockwise direction. This is clockwise and this is anti-clockwise. Okay, now this is my cello tab and if I am applying a force here, now it is moving in clockwise direction. Okay, this is clockwise. This is clockwise. Okay, so when the force is applied in opposite direction, it will be moving in anti-clockwise direction. Okay, so here if the effect on the body is to turn it anti-clockwise. Now here I am applying the torque to turn it anti-clockwise. Okay, the moment of force is called anti-clockwise momentum. In that case, the moment of force is an anti-clockwise moment. Okay, and it will always be taken as positive. If it is in the anti-clockwise direction, it will be taken as positive. In that case, the moment will be taken as positive. Okay, while if the effect on the body is to turn it clockwise, this is a body. Here I am applying force, applying torque. How it is moving? It is moving clockwise. In that case, the moment of force is called clockwise moment. And then it will be taken as negative. Understood what it is? Anti-clockwise. If the effect is anti-clockwise, to move it anti-clockwise, then the moment is anti-clockwise moment and it will be taken positive. In the other case, it will be taken negative. Okay. Now, the direction of rotation of a body can be changed by two ways. Okay. What are the two ways? The point of application of force. Okay. First one is by changing the point of application of force. Now, take the case of the steering. Here, I have a point A and a point B. First, my point is A. I am applying a force like this. Okay, this is how I am applying a force. What happens? In which direction it rotates? It will be moving this way. Okay. In this way, is it clockwise or anti-clockwise? This is clockwise movement. Okay. Here there is an anti-clockwise. Here we have a clockwise motion. Okay. When the force is applied at A. Now, the same force I am applying at this point B. What happens? How does it move? When force is applied like this, just imagine the case of the steering. How does it move? It will be moving in this direction. Is it clockwise or anti-clockwise? This is how the needle inside a clock moves. So this motion is clockwise and this motion will be anti-clockwise. Here the motion is anti-clockwise. Okay. So this is what? When the point of application of force changes, we'll be getting anti-clockwise and clockwise moment. Okay. Here it is anti-clockwise. In this case, at point A we got clockwise and at point B, by applying force, we got anti-clockwise. Okay. Next, second is by changing the direction of force. That is also very simple. Now take this case. Here I have the sellotape. I am applying force from this direction. What happens? It is moving like this. Okay. Here this is my sellotape. I am applying force in this direction. How is it moving? It is moving this way. Is it clockwise or anti-clockwise? Clockwise. Point is same. Okay. At this point A I am applying. Here the motion. It is clockwise. Clockwise motion. Clockwise rotation is happening. Okay. Next, I am applying force at this point A but in a different direction. From this direction. Initially this was how I applied force. Now I am applying force in this direction. That is, the rotation is in opposite direction. What happens when a force is applied here? What happens? The body starts moving in this way. Okay, the rotation will happen in this way. In that case, we have anti-clockwise direction. Understood? So, the two factors on which it depends, that is, the rotation of a body can be changed by two ways. The one is by changing the point of application of force. This example, A and B points. At A point, we got clockwise and B point, the rotation was anti-clockwise. Second is by changing the direction of force. Changing direction of force. Force is applied at same point, one from this direction and one from this direction. In both the cases we got, in one case clockwise and the other case anti-clockwise. Okay, let us take some examples of moment of force. The first example is to open or shut the door. Okay, here this is a closed door and we are opening a door. What are we doing? We are applying a force. Where is the force applied? We are holding the handle and either pushing or pulling. Okay, why the handle is chosen? We have discussed this. Yes, handle is at maximum distance from the hinge. Okay, here if you have a hinge, this is the pivoted point. Okay, we have points A, B, C. Clear? Same force is applied. What happens? When the force is applied at A, it is easier to open the door because the rotation, the turning effect is maximum when force is applied at A. We are applying same force. Okay. At point B, it is somewhat difficult. Why? Because the distance is decreasing. Distance is decreasing. Third point, there is no torque. Right? This C I have considered on the axis of rotation. In that case, we know torque is equal to force into perpendicular distance. Okay. First case, let us take, this is at a distance of some 30 centimeter. Second case, it is 15 centimeter. And this point C, it is at 0 distance. It is on the axis of rotation, which means the distance is 0. In the first case, what will be the torque? Torque when force is applied at A will be equal to, let's say 10 Newton force is applied. Okay, 10 Newton force into the distance. Distance here it is 30 centimeter, which means 0.3 meter. We will be getting 3 Newton meter as the torque. Second case, when the force is applied at point B, the torque will be equal to 10 Newton force into 0.15 meter. 15 centimeter is 0.15 meter. Okay, 0.15 meter is a perpendicular distance. Then what we are getting? We'll be getting 1.5 Newton meter as the torque. Third case, when force is applied here, that is, you are going to this end, you are pushing the door at the hinge. What happens? Will the door open? No, right? It won't open. Why? Because the perpendicular distance in this case is equal to 0. Whatever be the force, however, like how harder you push, it won't give you any result. Okay, 0, that is 0 Newton meter. So by applying a force on the hinge, you cannot open the door. Clear? Okay, to open the door, force should be applied at the handle because handle is at maximum distance. So this is your first example. Second example, turning of a steering wheel. How it is turned? How is the rotation happening? If I am applying a force at A, what happens? The body starts rotating, that is, it can move in this direction. This is how my force is applied. I am applying force like this. What happens? It starts moving in this direction, that is in clockwise motion. So force is applied, there is a perpendicular distance. Okay, if I am applying force in the same direction but at point B, what happens? Here the rotation will be in this direction and it is going to be anti-clockwise. Anti-clockwise rotation. Okay. At A, if I am applying force in this direction, what happens? The body starts moving, starts rotating. How is the turning effect? It will be going like this, which means again it is anti-clockwise. Okay, so this moment of force or the torque effect can be experienced by turning of a steering wheel. This is your second example. Third example is spanner which is used to tighten or loosen a nut. Okay, here you can find a nut. This is a spanner. Now, here the person is applying force at the end of the spanner. Why not here? Or why not here? You know the answer. Tell me. Yes, that is when he holds a spanner here, there is maximum distance, perpendicular distance becomes maximum. And with less force, he can either open or close it. Okay, so in order to open this nut, what should be done? He will be moving the spanner in this direction, that is anti-clockwise. Okay, in order to open, he will have to move in the anti-clockwise direction. Okay, force is applied, there is a perpendicular distance, the turning effect is produced, there is a torque or moment of force. Okay, next, in order to tighten it or close it, what is to be done? He will have to move in this direction, right? In this direction means the clockwise direction. Again, force is applied by him. Then, there is a perpendicular distance. The screw is tightened. There is a turning effect. The turning effect of the spanner is tightening the screw. Okay, you can do this even by applying force at this point. Applying force at this point also, you can open it and close it. But what is the difference? You will have to apply more force. Okay, more force will have to be applied. Why? Because in this case, the distance has decreased. Okay. Fourth example is turning the rear wheel in bicycle. Okay. In bicycle, what we are doing? We are applying force? We are pedaling, right? While pedaling, you are applying force. That is, the pedal will be moving in clockwise. That is, here, in this case, the cycle is kept in this direction, which means it is moving in the clockwise direction. The pedal is moving in the clockwise direction. Then what happens? Due to this pedaling, clockwise direction motion, what happens? The toothed wheel will start rotating. It will also move in clockwise direction. Then there will be a chain between this, which connects this toothed wheel and the rear wheel. Okay, so the effect will also be produced here. This will start moving in clockwise direction. And this is how the bicycle moves. So, the motion of bicycle has the effect of torque. Force is applied perpendicular. This is the pivot, right? Okay. Perpendicular to this, we are applying force. It is producing a turning effect or a torque, which helps in the movement of the bicycle. Next topic is couple. Do you think a single force is causing all this rotation? When you took the case of a door, here you have the hinge, okay? You are applying a force at the handle. What is happening? By applying the force, the door is getting opened. What actually happens in this case is when you apply a force in this direction, okay, an opposite force of equal magnitude is being applied, a reaction force is being applied by the hinge, and this two forces together can cause the rotation, okay. It's not just a single force involved. There is a pair of force. Okay. A pair of forces is causing this rotation effect, and we call this pair of forces as couple. Okay. Two equal and opposite parallel forces not acting along the same line form a couple. Okay. And it can produce a rotation. Now go through all these examples. First case with the steering. In case of steering, you can rotate it, you can turn it, you can produce a turning effect just by applying a force with one hand. Okay, you can just handle it with one hand, but it is more easier when you use two hands. Okay, when you move one part like this, the other will go like this. It is more easier, right? So applying the force from both the hands, it is more easier to cause the turning effects. Take all the examples. For example, I have a key. Okay, how to open a lock? What do? We put it inside. Key is put inside. Then we apply force. How is the force being applied? I am applying a force with this finger, that is with thumb. I will be moving it towards the right. And with this forefinger I am holding it, and this forefinger will be applying force towards the left. That is in opposite direction, equal forces applied, and then we can use this key to unlock. Okay. Take the case of a pipe. Is it this way you open a tap? Is it? Only one part you will be holding? No, right? You will be holding with your two fingers. That is, when forefingers is used to push it backward or forward, then the thumb will be used to move it backward. Only then the pipe will be opened easily. Even with one finger you can do just by applying force, but it is more easier when you use both these fingers in opposite direction, applying the same amount of force. Take the case of this water bottle. Is he using just one finger? Even with one finger it can be done, but it is more easier when both the fingers are used. I have a water bottle. I need to open this. What can be done? I can apply force with just one finger. I am just using thumb, but it is difficult for me to open. Okay. Now I am using two fingers, that is my thumb and my forefinger. Let me see here. I am holding my thumb at this point and my forefinger at this point. Now what happens? I am applying a force backward with this thumb and a force forward with this forefinger. It is more easier to open. When I tried with one finger, it was difficult to open, but when I tried with two fingers, it was easier to open. Clear? So this is what the idea of couple is. It is a pair of forces which is acting in opposite direction. Okay, magnitude will be same. Clear? Moment of couple. Now consider a bar. Here I have a bar AB. Okay, pivoted at point O. Forces are applied. This is force applied at point A, and this is a force applied at point B. Okay, when a force is applied at point A, it starts moving in this direction, right? This is how it should move. It is pivoted at O. Okay, what type of motion it is? Here we can produce an anti-clockwise rotation. Anti-clockwise rotation. Now check this case. Here from B, an upward force is applied. Okay, this is how the movement will be. This is how the rotation will be. Again, here also you have an anti-clockwise rotation. What is the perpendicular distance between the forces? The perpendicular distance between the forces is AB. Okay. This perpendicular distance between forces AB will be called coupled arm. Okay. And it is taken, the distance is taken as D. Okay. We have force at A, force at B, and the perpendicular distance between the forces AB, which is called coupled arm. Now tell me, what is the moment of force at A? Moment of force at A. How do we calculate moment of force? Yes, moment of force or torque is equal to force into the perpendicular distance. Here, moment of force at A will be force F into, we are said at both these points A and B, equal force F is applied. F into perpendicular distances from the pivot, the distance of the point of application of force. Okay, this is the distance which is OA. F into OA. Okay, next tell me what is the moment of force at point B. Again it will be force into perpendicular distance. Here it is OB. Okay, F into OB. Okay, now you have to find what the moment of couple is. Moment of couple. Couple is being formed with both these forces, force at A and force at B. This pair of force is producing a couple. So it will be the sum of both these moments. Yes, moment of force at A plus moment of force at B, which is F into OA plus F into OB. Take common, force is common, force into OA from this, OB from this. Okay, F into OA plus OB, which is equal to F into, what is OA plus OB? OA plus OB will be equal to AB. F into distance D. Okay, therefore we can say that this distance D is the coupled arm. It is the product of either force, any of the force, because both the force are of equal magnitude. Either force, you just need the magnitude of force into the coupled arm or the distance between the application, points of applications of forces or the perpendicular distance. You can have moment of couple is equal to either force, any of the force, into perpendicular distance between two forces, which is otherwise known as coupled arm. Okay, coupled arm. Moment of couple is equal to either force into perpendicular distance between the two forces. Okay, understood how to find the moment of couple? Next topic is equilibrium of bodies. The word equilibrium, you all know, right? What is equilibrium? Okay, now if you have a body and the body is free to move, it will be moving in a translation motion, right? A body is at point O, or let's say a ball is at point O. This is the direction in which force is applied. It is free to move. It will be having a translation motion. Okay. Now, if it is pivoted at a point, what happens? Then applying a force here will cause a rotation motion. But there are instances where when force is applied, there is no motion caused. Either translation won't happen nor there is rotation. Do we have any such cases? Consider this example of tug of war. Okay. Here we have 3 children. Here also we have 3 children. Both of these teams are applying equal force. In that case, does this rope move? Tell me. No, right? When equal force is applied, what happens? The effect of both these forces gets cancelled out. Let us say 3 Newton force is applied in this direction by team A and 3 Newton force is applied by this team B. Okay. Now, the force is equal in magnitude. But what is the difference? It is in opposite direction. Then the effect gets cancelled. Okay. And the body, that is here the rope does not move. It is said to be in an equilibrium. Got the idea of equilibrium? It is not necessary that there is only two forces. It can be any number of forces. But there is no motion produced. There is no movement caused. Okay. When a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. Okay. If it is having a rotational motion, it will continue to be in the same motion, or the linear motion, it will be continuing. There is no change caused to it. It's change of rest, or there is no change in its state of linear or rotational motion. Okay, in that case, the body is said to be in an equilibrium. Got it? Okay, we'll be discussing two kinds of equilibrium. The first one is static equilibrium. Static equilibrium. Okay, and the second one is dynamic equilibrium. Static equilibrium and dynamic equilibrium. First one, static equilibrium. When a body remains in the state of rest under the influence of several forces, the body is said to be in static equilibrium. With a simple example, we will understand. So here, this tug of war is an example of static equilibrium. So here, what is happening? All these children are applying force. All of them are pulling the rope. Is there any change in its position? Is there any change in its state of rest? No, right? It is said to be in static equilibrium. Okay. N number of forces are being applied, but the effect is there is no change in state of rest. You have a table. Okay. You have a table here. A boy is pushing the table with 5 Newton force. What happens? The position changes. It shifts to a new position. Okay. The same table is being pushed by 2 boys with same force, 5 Newton. First boy is applying 5 Newton. Second boy is also applying 5 Newton. What happens in this case? The distance travelled increases. Okay. The table can move greater distance because it is getting more force. Third case is, here you have the table. First boy is applying 5 Newton from this direction and second boy is applying 5 Newton from the opposite direction. Now what happens? Tell me. Does this table move? No, right? What is the reason? 5 Newton force is applied. Okay. But what happens? The effect gets cancelled. When you take the sum, one force is applied in this direction and the second force is applied in opposite direction, which means 5 Newton and 5 Newton get cancelled. 5 Newton plus minus 5 Newton. Okay, direction is important. In that case, you will be getting 0. The body, that is the table, does not move. Take another case. You have a bar supported on a fulcrum. Okay, you are keeping a box of 3 kg here and a box of 2 kg here. Okay, from this center O, let this distance be equal to 2 meter and this distance be equal to 3 meter. Okay, now tell me, is there any rotation caused in this case? So when you support a body like this, it should move downwards, right? That is, a rotating effect should be produced. But here we have a pivot. Okay. Here also it should move downwards. Now here this rotation should be in this direction, which is anti-clockwise. And here it will be in this direction, which is clockwise. Will this rotation happen? I want to know. Anti-clockwise moment. Tell me, what is the anti-clockwise moment in this case? Force into the distance. Okay. Here what is the force? It is a mass of 3 kg. Force will be the weight of body, which means the 3 kg mass into the acceleration due to gravity. So 3g will be the force. Okay. 3g will be the force. Distance is 2 meter. 2 meter, which means 6g Newton meter will be your 6g Newton meter will be your anti-clockwise moment. Okay. Now consider this part. Here a 2 kg mass is kept at a distance of 3 meter. Okay. Rotation will be clockwise. So clockwise moment will be equal to, here the weight is 2 kg into acceleration due to gravity, which is 2g into distance. Distance is 3 meter. 3 meter, which is equal to 6g Newton meter, where g is equal to 9.8 meter per second square is the acceleration due to gravity. Okay, here we are getting 6g and here also we are getting 6g, which means the torque is same. Okay, therefore the anti-clockwise moment is equal to clockwise moment. And there is no rotation caused in this case because the torque on both these cases, the torque is same. So no rotation will be caused. Okay, understood this example? So this is what static equilibrium is. Here no rotation is caused. Here the table does not move. Here the rope does not move, even though force is applied. Okay. Second kind of equilibrium is dynamic equilibrium. When you took the case of static equilibrium, the body will remain at rest. Okay. Take the example of a book which is kept on a table. The book will be applying a downward force, which is the weight of book. And the table will be applying a force in the upward direction. Okay, which is equal and opposite to the force applied by book. And the book does not move, book does not fall down. Now take the case of dynamic equilibrium. When a body remains to be in a state of motion, it can be translational or rotational. Under the influence of several forces, the body is said to be in dynamic equilibrium. This is the main difference. In static equilibrium, the body will be at rest. When it comes to the dynamic equilibrium, the body will be in a state of motion. Take the case of a raindrop. Okay, when a raindrop comes down, do you think the velocity of the raindrop is increasing? When you put a bowl down, what happens? It starts moving and the velocity starts increasing. That is why when it reaches the ground, there is a bouncing effect. But with the case of a raindrop, the weight is acting downwards. Okay, weight of raindrop is acting downwards. To balance this, there is two other upward forces. Okay, when weight acts downwards, you have the friction due to air resistance. The frictional force will be acting upward, and also the buoyant force or buoyancy. What is buoyancy? Buoyancy will also be acting upward. What is buoyancy? Buoyancy is an upward force in case of fluids experienced by the body. Okay, a body which is immersed in a fluid will be experiencing an upward force, and this upward force is called buoyancy. So this weight will be balanced by the frictional force and buoyancy. Okay, and therefore the velocity with which the body, that is the raindrop, is moving will remain the same. It will be moving with a constant velocity. Clear? So this is an example of dynamic equilibrium. Here we can see translational motion. Okay, the body does not come to rest. Since both these forces, that is weight and the buoyant force and friction, is being balanced, does the raindrop stay somewhere there? No, right? It will be coming down with a constant velocity. Take the case of an aeroplane. Aeroplane, after reaching a height, the weight will be acting downwards. When weight acts downwards, there is an upthrust which is acting upwards. Here again, the aeroplane can be moving at the same height because both of this gets balanced and the aeroplane is said to be in a dynamic equilibrium. This is again an example of translational motion. Okay, it continues to be in the translational motion. An electron which is revolving round the nucleus in an atom, or planets revolving round the sun, are also examples of dynamic equilibrium. There is no net force, that is the net force which is acting on this electron will be equal to 0. Okay. Therefore, the body continues to be. Here the body is the electron. Electrons continues to be in its motion. It doesn't come to rest because more forces are acting on it. It doesn't come to rest. It keeps on moving with its constant velocity. These are examples of dynamic equilibrium. Here we have the two conditions for equilibrium. Conditions of equilibrium. One is the resultant of all forces acting on a body should be 0. Just take the example of the static case. Here we are applying 5 Newton force from this direction, 2.5 Newton. One person is applying from the opposite direction and 2.5 Newton. Another person is applying from the opposite direction. When you take the algebraic sum of this, so here 5 Newton force is applied in one direction. When you take these two forces, it should be taken negative because they are in opposite direction. So minus 2.5 Newton minus 2.5 Newton. What is the resultant force? Resultant force will be equal to 0. Therefore, the resultant of all forces acting on the body should be 0. Okay. Next condition is the algebraic sum of moments of all the forces acting on the body about the point of rotation should be 0. Just take the case. If a body is pivoted at this point, okay, many forces are applied. Some forces are applied like this. Some are applied like this. Some are applied like this. When you take the algebraic sum of their moments, the algebraic sum of moments should be equal to 0. When it is being rotating, it can have clockwise moment and anti-clockwise moment. Therefore, the algebraic sum of clockwise moments should be equal to the algebraic sum of anti-clockwise moments. Okay, they should be equal. Clear? So these are the two conditions of equilibrium. Principle of moment. The last topic we are discussing today is principle of moment. It is nothing, just a statement. If the algebraic sum of all the forces acting on the body about the axis of rotation is 0, the body is said to be in equilibrium. This is a statement for principle of moment. According to principle of moment, in equilibrium, the sum of anti-clockwise moment should be equal to the sum of clockwise moment. This also we have stated. Okay, and the beam balance will always work under this principle of moment. Now take the case. Here you have a meter rule which is supported at point O. Now using spring balances, weight W1 and W2 is suspended at points A and B. A is at a distance L1 and B is at a distance L2. We are going to verify. This is a verification for principle of moment. Okay. Now what happens? This weight W1 is more. Okay. And in that case what happens is there may be a tilt. Okay. Here you have the horizontal meter rule. What happens? More weight is applied and the distance is very large. In that case what may happen? The body can bring a rotation. This weight can bring a rotation and this rotation here it is clockwise. Okay, clockwise rotation is happening. Now, if it is the tilt is happening in this direction, that is here due to this weight W2, the tilt may happen and the rotation may happen in anti-clockwise rotation. The rotation will be anti-clockwise rotation. Because of W2 anti-clockwise and because of W1, the rotation may be clockwise rotation. Okay, just imagine the case. If there is no weight at point B, then what happens? Even if you hold with the support, the body will move. That is, this point A with weight W1 will move in a clockwise motion. There will be a tilt. Okay, if there is no weight at A, then what happens? The B may be moving down. That is showing an anti-clockwise rotation. Now tell me, what is the clockwise moment? Clockwise moment will be equal to the weight into, here the weight is W1 into perpendicular distance. Here it is OA, which is W1 into L1. What is the anti-clockwise moment? Anti-clockwise moment will be equal to weight W2 into the perpendicular distance OB. W2 into L2. Okay. What we have to prove? We have to show that the sum of clockwise moment is equal to the sum of anti-clockwise moment. When this meter rule is horizontal, that is balanced, it is like this. Okay, there is no tilt. In that case, there is a balance. It is only when W1 L1 is equal to W2 L2. When you take this moment, that is a clockwise moment, it becomes equal to anti-clockwise moment, then there will be a balance. That is, it will be, the meter rule will be horizontal. So, we have proved that the anti-clockwise moment is equal to clockwise moment. Okay, anti-clockwise moment is equal to clockwise moment. The meter rule is brought to an equilibrium. Understood? So, this is the proof for the principle of moment. Okay, let us do some problems from the numerical part. Problem 1. The moment of a force of 10 Newton about a fixed point O is 5 Newton meter. Calculate the distance of the point O from the line of action of the force. We have to find the perpendicular distance. What is torque or moment of force? We have moment of force or torque is equal to force into perpendicular distance. Okay, that is F into R. We have to determine what R is. R will be equal to torque divided by force. Okay, what is the torque here? Torque is given 5 Newton meter. 5 Newton meter divided by the force. Force is 10 Newton. Okay, 5 divided by 10 is 0.5. Okay, Newton and Newton gets cancelled and the unit of distance is meter. Therefore, the perpendicular distance, that is the distance of the point O from the line of action of force, will be equal to 0.5 meter. Very simple. Just remember this. Torque is equal to force into perpendicular distance. If force and torque is given, we can find perpendicular distance. Perpendicular distance and torque is given, we can find force. And when torque and force is given, we can find the perpendicular distance. Okay. Second problem, a steering wheel of diameter 0.5 meter is rotated anti-clockwise by applying two forces each of magnitude 5 Newton. Draw a diagram to show the application of forces and calculate the moment of the force applied. Here you have a steering wheel. This is the diameter, which is 0.5 meter. Okay. Now two forces are applied. Here this is your first force of 5 Newton and the second force of 5 Newton. How to calculate the moment of force? Moment of force is equal to any of the force, either force into perpendicular distance between the point of application of two forces, which we also call coupled arm. That is F into D. This distance is taken D. Okay, coupled arm is taken D. Now what we have to do? We have the force given. Force is equal to 5 Newton. Both the forces are equal to 5 Newton. What is coupled arm? Coupled arm D is equal to 0.5 meter. We know that diameter is the longest chord. Okay. So here the perpendicular distance between the two forces will be the diameter, which is 0.5 meter. Coupled arm D is equal to 0.5 meter. So this is the required diagram. Now we'll find what the moment of force is. Moment of force or torque is equal to F into D. F is 5 Newton into D is 0.5 meter. 5 into 0.5, we will be getting 2.5. What is the unit? Unit of torque. Newton meter. Correct. Newton meter. Okay. 2.5 Newton meter is your moment of force. Clear? Problem number 3. A uniform meter rule is pivoted at its midpoint. A weight of 50 GF is suspended at one end of it. Where should a weight of 100 GF be suspended to keep the rule horizontal? Here we are going to use the principle of moments. Okay. You have a meter rule. The total length will be 100 centimeter. 1 meter is equal to 100 centimeter. In this meter rule, a weight of 50 GF is suspended at one end of it. Okay, here it is pivoted at the center. One end of it you have 50 GF. So here we have O, this point is A, 50 GF weight is suspended here. Okay, what is this distance? If in this meter rule it is pivoted at the center, at the midpoint, then this distance will be, total we have 100 centimeter, this distance will be what? 50 centimeter. This distance will be 50 centimeter. Now what is the question? We have to find where a weight of 100 GF should be suspended to keep the rule horizontal. So when you suspend this 50 GF, what happens? It will cause an anti-clockwise moment. Okay, an anti-clockwise rotation or an anti-clockwise moment is created here. In order to balance this, to keep it horizontal, what should be done? A weight should be suspended here, but we need to find where the weight should be suspended. According to the principle of moment, we are having the sum of anti-clockwise moment will be equal to sum of clockwise moment. Anti-clockwise moment sum will be equal to clockwise moment sum. Here 50 GF is producing a anti-clockwise moment. What is it? Let us take the first weight W1 and the distance L1 will be equal to W2 L2. Here W1 is the first weight, which is 50 GF. 50 GF into distance L1 is 50 centimeter equal to W2. W2 is the second weight, which is 100 GF into L2. L2 is what we have to determine. At what distance this 100 GF is suspended. Okay. How to find L2? L2 will be equal to 50 GF into 50 centimeter divided by 100 GF. Okay. 50 by 100. You will be getting 2 here. So 50 centimeter divided by 2. This units can be removed. 50 centimeter by 2. What is the answer? 25 centimeter. So at 25 centimeter, 100 GF weight should be suspended to keep the meter rule horizontal. Okay, in order to keep the meter rule horizontal, when 100 GF weight is suspended at 25 centimeter from the pivot. Clear? Then the rule will be horizontal. Okay. Problem number 4. A physical balance has its arms of length 60 centimeter and 40 centimeter. What weight kept on the pan of the longer arm will balance an object of weight 100 GF kept on the other pan? Okay, here we have the physical balance. Okay, the arms of length. One is 60 centimeter and the second is 40 centimeter. Okay, the longer arm is the 60 centimeter one. What weight kept on the pan of the longer arm? Here we have to find the weight kept on the longer arm will balance an object of weight 100 GF which is kept on the other pan. Okay, here the 100 GF weight is kept. How to find? Using the principle of moment, we have clockwise moment equal to anti-clockwise moment. So when 100 GF weight is kept at this span, what happens? It will be producing clockwise or anti-clockwise? Correct. It will be producing a clockwise rotation, or it will produce a clockwise moment. Okay. And this will produce anti-clockwise moment when a suitable weight is suspended. Let's see. We have W1 L1 equal to W2 L2. Here W1 is 100 GF. L1 is the distance. Here it is 40 centimeter. W2 we need to find, and L2 we know, which is the longer arm, 60 centimeter. Put the values. W1 100 GF. L1 is 40. W2 we don't know. L2 is equal to 60. Then what is W2? 100 GF into 40 by 60. How much do we get? You can cancel the zeros. So that is W2 is equal to 4 by 6 into 100 GF. 4 by 6. How much do we get? 0.6667. It goes on. Okay. Into 100 GF. So somewhat your answer will be 66.67 GF. So this is the required weight which should be kept on this span. Okay, in order to bring to a balance. Clear? Just we have used the principle of moment. Very easy, right? That's all for today. In today's class, we have discussed what force is, what is motion, types of motion. We have discussed about torque or moment of force. We have discussed what couple is, equilibrium, kinds of equilibrium, and at last we have discussed the principle of moment. We have also solved questions related to it. Hope you all enjoyed this session. I'll be back in the next session. Until then, stay tuned to LearnoHub. LearnoHub free hai par best hai. Thank you.